Welcome to section 7.3. Our main focus today is going to be finding the Laplace transform of derivatives, but we're going to start off with a quick review of how to use our table. So in this first one, I want to use formulas 2 and 5, and in formula 2, n is equal to 1, and in formula 5, n is 2 and a is 3. And so this is simply equal to 3 over s squared plus 2 over s minus 3 quantity cubed. Okay, next one, I want to use formulas 6 and 12. So number 6, b is 2, and number 12, b is also 2. And so just by reading those formulas, this is 2 over s squared plus 4 plus 4s over s squared plus 4 quantity squared. Notice the difference between formulas 6 and 7. One has a b on top and one has an s on top. You'd think sine would have an s on top since sine starts with an s, but it's actually cosine. Okay, now we're going to find a formula for the piecewise defined function pictured here. So this is a skill we're going to need. This is just algebra, but it's always a good review. So f of t is going to be 0 if t is between 0 and this point here, which is 2. So 0 less than or equal to t less than 2. Now here, this can be less than or equal to or strictly less than. It doesn't matter. Over here at the 2, we do want strictly less than. And then after that, the function becomes this line. Well, the slope of this line, if I go 1 over and 2 down, m is negative 2. And then if I use point slope, y minus 4 is negative 2 times t minus 2. Solve for y, and that gives me y equals negative 2t plus 8. So that's what I want here. Negative 2t plus 8, and that's for t greater than 2. Okay, first translation theorem, this won't take us long at all. First translation theorem relates the Laplace transform of a function to, so over here in this graph here, Laplace transform of a function to the Laplace transform of that same function times e to the at. So it's easiest to see it with an example here, comparing formulas 3, 6, and 7 to 5, 8, and 9. Look what happens to the Laplace transform, for example, of t to the n. When I multiply by e to the at, it's the same formula except with s replaced by s minus a. And so I've got a proof of this theorem at the end, but you really don't need the theorem because it's built into our table. 5, 8, and 9 build that theorem in. So for example, if we want L of e to the 4t cos 5t, we're just going to use formula number 9 with a equal 4 and b equal 5. And so that's just s minus 4 over s minus 4 quantity squared plus 25. Okay, transforms of derivatives. In your table, if you look at your Laplace transform table, you'll see formulas 19, 20, and 21 stated like this with L of f prime, f double prime, f triple prime. Typically, we're going to want to use these three forms over here, L of y prime, y double prime, y triple prime. Seldom will we be doing y triple prime, but mostly we'll be using formulas 19 and 20. I have a proof of formula 19 at the end that uses integration by parts. It's not difficult, but let's apply these formulas. If y of 0 equals 2, find L of y prime. All right, so L of y prime by formula 19 is s big Y, and make sure I can tell your big Y from your little y, s big Y minus y of 0. Okay, so that's s big Y minus 2. Piece of cake. All right, L of y double prime, I'm going to use formula 20. That's s squared big Y minus s y of 0 minus y prime of 0. Okay, well that's s squared big Y. Y of 0 is 1, so minus s, and then plus 2. Okay, typically we're going to want the Laplace transform of a linear combination of derivatives. So in this example, I want L of y prime, and I'm going to subtract 2 L of y by linearity. All right, well, L of y prime is s big Y minus y of 0, and this is minus 2 L of y. Well, you won't see that in the table. By definition, L of little y is big Y. L of little y is big Y. Okay, and that's s big Y plus 3 minus 2 big Y. And then we're just going to combine like terms, s minus 2 big Y plus 3 is what we have, okay? And eventually what we'll be getting at is solving differential equations with Laplace transforms. So we're going to want to take the Laplace transform of both sides of a differential equation, and that's what we're going to do here in this example. So we want L of y double prime plus 2y prime, and we're going to set that equal to L of 0. So I took Laplace transform of both sides. Now, on the left, I have s squared big Y. I'm just going to write down the general formula for L of y double prime. S y of 0 minus y prime of 0, and then plus 2. L of y prime is s big Y minus y of 0. All right, and that's equal to L of 0. Again, this is not something you're going to see in the table, but if you look at the definition of a Laplace transform, L of 0 is just 0. All right, now let's fill in the numbers we're given. This is s squared big Y minus 2s plus 1, and then plus 2s big Y. I'm going to distribute the 2 minus 4, and that equals 0. Now I want to solve for big Y. So everything with a big Y in it is going to stay on the left. I have a big Y, and then let's factor out. We're going to have an s squared plus 2s. Everything without a big Y in it moves to the other side. So I'll have a 2s, and then combining like terms, I have a negative 3 on the left. That'll move over as a positive 3 on the right. So finally, moving up here, if I want to solve for big Y, that's 2s plus 3 divided by s squared plus 2s. Now, in terms of solving a differential equation, I just want to remind you of where we are in this picture here. Instead of little x prime, we're using y prime. And so instead of big X, we've got big Y. We're taking the Laplace transform of both sides of a differential equation, and then we're solving for big Y. And then eventually we're going to take the inverse transform and do this leg. So right now we're on legs 1 and 2. Okay, back to the lecture. We're going to do one more example involving derivatives, and then we're going to do a preview of finding inverse transforms. So our goal here is to find big Y over big G. So we start by taking Laplace transform of both sides of this differential equation. L of y double prime plus 4y prime plus 6y equals L of little g. Okay, we're told all the initial conditions are 0. That means we're told y of 0 is 0, and y prime of 0 is 0. So formulas 19 and 20 are going to simplify greatly. In fact, L of y double prime is just going to be s squared big Y, and the other two terms will be 0. So I'll have plus 4. L of y prime will just be s big Y, and then L of 6 little y is 6 big Y. And then on the right, what's L of little g? Well, by definition, that's big G. L of a little variable is always the big variable. So I'm going to have to pull out a big Y on the left, and I'll be left with s squared plus 4s plus 6, and that equals big G. And I want big Y over big G, so this implies big Y over big G is going to be 1 over s squared plus 4s plus 6. So you have one in your homework like that, and it's a little bit odd wording, so I thought I'd go through that with you. Okay, preview of finding inverse transforms. This is sort of where the art comes in. So we can read our table forwards to find Laplace transforms, and we can read it backwards to find inverse transforms. So for example, if I want L inverse of 1 over s cubed, well, my starting point is that I know L of t squared, this looks closest to me like formula 2, L of t squared is 2 factorial, which is 2, over s cubed. And so I can just do a little bit of massage. So thus, L of 1/2 t squared would be 1/2 2 over s cubed, which is 1 over s cubed, which is what I want. So L inverse of 1 over s cubed is 1/2 t squared. And you can do most of what I just said and wrote down in your head. All right, for B, this looks to me like formula number 3 with A equal -4. So this is simply equal to e to the -4t. Now be careful with your variables. When you go forward, you go from t's to s's. When you go backwards, you go from s's to t's. Okay, the next one looks to me like number 6 except 6 has a b on top. My b here is clearly 2 because 2 squared is 4. I don't want a 2 on top. I want a 1 on top. So what I'm going to do is do 1/2 sine of 2t. And that 1/2 will get rid of the 2 I'll get on top when I take the forward transform. Okay, and then the last one, d, this to me looks closest to formula number 5 with n equal 3. So if I just started out with, let's say, t cubed e to the 2t, if I took the Laplace transform of that, I would end up with a 3 factorial on top. I've got a 1 on top, so I'm going to put a 1/6 out here, and that will do it. And so you can see it's a little bit of an art, but you'll get used to it. And that is the end of this section.